And you know this already when you see ice skaters. When an ice skater spins and they want to spin faster, they start with their arms outstretched. And they have a certain rotation speed by virtue of that. As they bring their arms in, this is a phenomenon of physics called the conservation of angular momentum. If you start out large, slowly rotating, and now you're half the size, you're going to be rotating twice as fast. If you're 1/10 the size, you're going to be rotating 10 times as fast. Is that right? mv squared over r. Right? This is why everything in the universe has some kind of rotation, because it's essentially impossible for any large gas cloud to not have motions within it to begin with. Often they're thermal motions. There's turbulence within the cloud before it sort of collapses to become something solid.
So why does the universe seem to prefer spinning, from pirouetting skaters to whirlpool galaxies? We look out and see rotation across many scales. Collapsing clouds that form stars often flatten into disks. Many galaxies carry angular momentum, some as grand spirals, others as rotating ellipticals, and even small asteroids can spin or tumble. Apparent stillness is fragile. Any tiny irregular motion gets amplified when something shrinks under gravity. Rotation becomes the stable way to store motion because it doesn't require matter to pile up at one place. It distributes motion around an axis. But ubiquity isn't the same as inevitability. Some newborn stars spin gently, others fiercely. Black holes can be nearly non-spinning or rotate close to the maximal rate permitted by general relativity. If spin shows up everywhere, that doesn't yet tell us what sets its amount. It just tells us the stage is welcoming to it. So the real puzzle is this. If motion tends to concentrate into spin when things shrink, what actually fixes how much spin a forming star or black hole ends up with? How can something conserved decide a final spin in the first place? Conservation applies to isolated systems. The universe rarely obliges. Torques, forces applied with leverage, shuffle angular momentum around. In the young cosmos, neighboring overdensities tugged on each other. That web of gravity imparted net spins to proto-galaxies, a process known as tidal torque. As gas fell inward, any residual twist sped up because the radius shrank. Now add a deeper principle, Noether's theorem. Because the laws of physics don't care which way you face them, angular momentum is conserved. That's why the universe prefers spin. Symmetry demands a ledger, and spin is the entry that doesn't vanish when the radius changes. But conserved doesn't mean locked to one object. Disks form to move angular momentum outward so mass can fall inward. Magnetic fields tie gas to space like invisible brake pads. Winds and jets carry spin away as exhaust. That's why the sun rotates slowly. Its magnetic wind has been bleeding spin for billions of years. Black holes spin up with coherent, steady accretion and can spin down with chaotic feeding or powerful jets. If spins are negotiated by these cosmic trades, can we read an object's biography from its spin? What does a spin reveal about the life it has lived? Galaxies aligned with filaments of the cosmic web suggest their spins were sculpted by the larger scale flows around them. When galaxies merge, orbital angular momentum can be converted into the remnant's rotation. One reason some ellipticals rotate differently from their progenitors. Neutron stars born in supernovae can start at tens of rotations per second. Spun up by companion-fed accretion, they become millisecond pulsars. Then, over millions of years, they slow as magnetic fields radiate energy and angular momentum away. Even Earth tells this story. Ocean tides raised by the moon transfer Earth's rotation into the moon's orbit, lengthening our day by about 2 milliseconds per century while the moon drifts outward. Black holes, measured via X-ray spectra from their hot disks when accreting and via gravitational wave signals when they merge, come with spins that hint at feeding histories. Near maximal spins are consistent with prolonged, coherent accretion, whereas the low effective spins seen in many LIGO-Virgo-Cagra events are consistent with either small intrinsic spins or misaligned orientations, as expected in more chaotic or dynamical environments. At the edge of physics, around rotating black holes, does spin merely move matter, or does it reshape spacetime? And how does conservation survive there? What does rotation do to spacetime itself, and where does the ledger balance? General relativity says a rotating mass drags spacetime around with it. In a Kerr black hole, frame dragging is so extreme that inside the ergosphere, everything is compelled to swirl. That's not metaphor. Satellites around Earth have measured a faint version of it with Gravity Probe B and LIGOS. Near a black hole, the effect becomes an engine. Magnetic fields tap into spin and launch relativistic jets, the Blandford-Znajek process, literally extracting rotational energy. In mergers, we've heard angular momentum leave as gravitational waves. Those ripples carry not just energy, but also spin. They're the courier that keeps Noether's promise even when matter disappears behind an event horizon. After a black hole merger, the remnant rings down, shedding the leftover wobble as space-time vibrations until a single, steady spin remains. So conservation doesn't buckle. It expands its jurisdiction to include fields and radiation. That's the shift in perspective. The universe doesn't prefer spin because it likes motion. It keeps spin because symmetry requires accounting, and interactions write the bookkeeping. Rotation is memory of every torque, every tide, every collapse. Read it well, and you can reconstruct how matter moved, how gravity sculpted, and how space-time itself participated. From skaters to stars to black holes, cosmic evolution is the steady redistribution of angular momentum, not the defiance of it. Like if this was interesting, and hit the subscribe for more.